change in inflection. There's no point there.
Change
Change from concave up to concave down. Change from concave up to concave down. That's a change in
Wait, that says is a
concavity.
point the curve where.
Concavity changes. Concave up to concave down.
Point.
A point. Oh, I left off the word on. That's the problem. That's where you're getting confused.
Yeah, I read it like 3 times, and I'm like,
That's
is my English not?
Alright, whatever. So.
That Polio compare.
Yeah, Polio compare was given to me.
So, for example, you might claim that in this picture there's a change in concavity right about there. Right about there. You know, change in concavity is hard to see pictorially sometimes, like exactly where it's happening. But you could claim that, you know, here all of the tangent lines lie above the curve, and then right here it's going to change and start to become below the curve. So there would be our change in concavity. That would be our inflection point. Okay? Here's concave down, and there's concave up. That's what you're looking for with the second derivative, okay?
Oh.
Conceptually, that's what you're looking for. Then I have to draw pictures. All right, so let's do that. That would be a problem like 47 through 56. So do 47 first. Should be easy enough. Place good pictures. 47. Determine the intervals on which the following functions are concave up or concave down. Determine intervals of concave up and concave down for functions. Five x to the fourth minus 20x cubed plus 10. F of x is 5x to the fourth minus 20x third minus 10. What is it?
Of what? CU? What is CU?
See me. What?
CU?
Concave up, concave down. F plus. Nope, that's not plus. I quit.
No, we need to finish this course.
All right, there is the function at hand. Determine intervals of concavity. And identify any inflection points. And find all inflection points. I'll spell this all out so that you guys can read abbreviations. So we need to talk about the second derivative. So you got to take two derivatives now. So f prime is what? 20x to the third minus 60x squared. You need to talk about the second derivative, which you need to find. So 60x squared minus 120x. Is that okay? Talk about second derivative. Okay. So now, if second derivative is positive on an interval, then the function is concave up. If the second derivative is negative on an interval, the function is concave down.
Will you say it again?
If the second derivative is positive on an interval, then the function is concave up, like an upward opening parabola along that along those locations. And if it is negative, it's concave down. So we are concerned where it's 0. We're concerned where it's neither of these. Okay? So again, very similar to the first derivative test. You got to set equal to 0 and find out where it's undefined. And you're going to plot those on a number line just like before. So now this function is defined everywhere. So the only thing I need to plot is the roots of this equation. What were you going to say?
I was going to say, can't you pull out that side?
Take out 60x. 60x left with x minus 2.
Yeah.
Yeah. Equal to 0. What's the solutions? X equals
0 and 2.
So that's what goes in your number line, just like the first derivative test. Again, this is not called second derivative test. It's called test for concavity. So now you put 0 and 2 on your number line. That is where the second derivative is equal to 0. All right? So that means every other location along these three intervals, it must be either negative or positive, which is what you're trying to find out.
And you put it into the original equation, right?
Put it
Plug
into
into the derivative.
Yeah,
Second
you're testing the sign on the derivative, on the second derivative, right?
Okay.
So take a number which is less than 0. Say what? It's defined everywhere. It's plot nominal. So you pick a number which is less than 0.
Negative 1.
-1. Plug it into. You got to make sure you keep the full derivative, second derivative expression, right? Don't chop the 60 off. You could divide by 60, right? Both sides, and you'd be clear for solving an equation. But what if this were -60? That would affect the sign when you're plugging in values. So you've always got to keep the full derivatives when you're plugging in numbers. All right? So now you plug in -1. Plug in -1. The outside becomes negative. This is negative. You get a positive. So along with this interval, second derivative is positive. So now you know along that interval, function is concave up. That's what you now know. The original function curves in a certain way. Pick the number 1. Plug it in, positive and a negative. So therefore negative. The original function is now concave down on this interval. Yeah, now you see why I write CU and CD. Just takes too much space. Pick number 3, it goes back to positive. A positive and a positive is positive. Here we go, back to concave up. Okay? So the function is like this, and then like this, and then like this.
You're plugging that into the 60x.
Correct, you've got to plug it into the full derivative.
Alright.
Meaning full, I'm saying second derivative, yeah.
Okay.
Yeah, second derivative. So now that you know this information, if the function changes concavity at a point, and that point is on the curve, that's called an inflection point. So did it change concavity from here to here?
Yeah.
Yes. Is 0 a legitimate value to put into the function?
Mm-hmm.
Yes, it's polynomial. So therefore 0 is an inflection point. Same question about this one. Did it change concavity at 2? Yes, because the signs of the second derivative changed. Is 2 a valid input into the function? Yes, it's a polynomial. So therefore, inflection point at 2. Right? So the intervals of concavity now, to write it out properly, that's just the test. So we'd have concave up from where to where? Negative infinity.
Negative infinity to 0.
Not inclusive, right? These are always not inclusives. Okay? Inclusive? Union, what? 2.
0 to 2.
No, 2 to infinity, right? Concave up? 2 to infinity.
And the concave down would be 0 to 2.
All right. Sounds good. Inflection point. Inflection point at what? 0, comma something, and 2, comma something. So you just plug the 0 into the original function to find the height of the inflection point. Looks like it's 10. You plug 2 in to find the height of the inflection point there. 2 to the 4th is 16 times 5 is 80. 2 to the 3rd is 8 times 20 is 160. So what was this number again? 80 minus 160 is 80 negative, plus 10 negative 70. Is that right? Did I do it right or not? So much way to compare, I can't think straight. Negative 70?
It's not the granola.
Negative 70? So there's our 2 inflection points, the 0, 10, and 2, negative 70. Any question about that problem? Sabru, yeah?
Yeah, what is the second one? Is it like under the critical value? Is it C?
Well, not critical value. CU, CD. Yeah, I'm changing the, yeah. CU and CD. CU, CD, input, inflection point. The last one is inflection points. Right? These are points. These are intervals, right?